So the final part of this chapter is chemical reactions and writing chemical equations. A chemical equation is just the symbolic representation of a chemical reaction in terms of chemical formulas. So if I said we're going to burn some sodium and chlorine together to produce sodium chloride, how would we write that? Well, sodium is a metal, and chlorine, the gas, is Cl2, and sodium chloride, NaCl, is the salt. Now, the numbers in front, the 2 in front of the sodium and the 2 in front of the sodium chloride, is called a coefficient, and to get those numbers you have to balance an equation, which is what we're going to do in a minute. So on the left-hand side, we have the reactants. Those are the things that we start with. On the right-hand side, we have the products. The arrow can mean yield. Sodium plus chlorine yields sodium chloride. Often you'll see information in the equation. So sometimes these things can be added. If you see a S, it means a solid, L, liquid, G, gas. If you see an AQ in parentheses, that stands for aqueous, which means dissolved in water. So if you put these labels in, you can see it adds just information to our overall equation. So 2 sodium solid plus chlorine gas gives us sodium chloride solid, 2 of them. Now, the coefficients come because of the law of conservation of mass. So the law of conservation of mass says that that matter can neither be created nor destroyed. Well, the easiest way to determine if matter has been destroyed or that matter is not destroyed or created is to make sure you have the same number of elements on each side of the equation. So they're rearranged, but you have the same number on both sides of the equation. So if the number on each side matches, then that equation is said to be balanced. So if we look at this equation, CH4 plus O2 gives us CO2 plus H2O. That is not balanced because we only have 4 hydrogen on the left, or we have 4 on the left, we only have 2 on the right. We have, the carbons are the same. There's only 2 oxygen on the left and there's 3 on the right. So this is not a balanced equation, and so what we're going to go through is how to balance an equation in the next few slides. This is the combustion of methane to produce carbon dioxide and water. All right, so this is a balanced equation. So now if you look at it, you can see and notice that a coefficient will distribute to everything that comes after it in that molecule. So you can see here on both sides we have 1 carbon. There's 4 hydrogen on the left, but now that we wrote the 2 in front of H2O, there's 2 H2Os, which means there's 2 times 2 or 4 hydrogen. On the left-hand side, we have 2 times 2 or 4 oxygen atoms, and you can see on the right we have 2 combined with the carbon, and then 2 times 1 for the waters, and so there's 4 oxygen. So now everything's balanced. So what's the process that we have to go through to get a balanced equation? Well, here's a step-by-step example where you can see what's going on. If we look at the initial equation, so H2 plus O2 gives us H2O, and what we want is the coefficients that go in front of them. So we can see just by looking at the molecules that on the right there's only 1 oxygen and 2 hydrogen. On the left there's 2 oxygen and 2 hydrogen. So if I want another oxygen, now you have to always think, it's very important that you always think multiplication. I'm going to multiply, I need 2 H2Os to get 2 waters on the right. I can't change the formula. Some of you might say, hey, just put a 2 after the O, right? H2O2. Well, what that does is changes the molecule. It's no longer water. It would be hydrogen peroxide. Well, if I wanted to make hydrogen peroxide, that would be fine. But I'm trying to take hydrogen and oxygen to make water, and so I can't change the formulas of any of the compounds that are there. I can't stick a 2 in the middle. I can't stick a 2 at the end. I can only change the coefficient. So if I put a 2 in front of the H2O, you can see now I've doubled my number of waters. So think multiplication. I have 2 waters. So now you can see that the number of oxygens have balanced because I have 2 purple circles on the left and 2 purple circles on the right. But in the process of doubling my waters, I now have doubled my hydrogens that were already balanced. So now I have 4 green circles or 4 hydrogen on the right, and I have 2 on the left. But I can now, if I double the number of hydrogen on the left, again, think multiplication. It's harder if you think add one more. Think multiplication. What do I need to multiply to get the same number? You put a 2 in front, and that's now everything's balanced. Let's do a few more examples here, and I'll give you some guidelines on the best way to balance an equation. So again, these are guidelines. They're not hard and fast rules, so you don't have to do it. And 2 people doing the same equation may do them slightly different, but I think these are really helpful guidelines that if you don't know where to start, this will help you. So I tend to start with the most complicated molecule. Or notice if some elements appear in more than one compound, like that last example, well, the CH4 going to CO2 and H2O, the oxygen showed up in 2 different places. So I tend to leave that for last, because if you're changing things around, you don't want to change one and then have to change the other. So if something shows up in more than one place, save it. If something just shows up in one compound on each side, then that's a good place to start. If an atom occurs by itself, I also save it for last because it's the easiest to fix without changing something else. Again, guideline number 3, which is actually, that is a hard, fast rule. Only change coefficients, never change the formulas. Coefficients should be the smallest whole number possible. So in fact, if you may end up multiplying everything by 2 or 4, and then you would have everything maybe higher multiples than what you need. So you should always check your equation at the end and make sure that there's not something you can divide everything by to reduce it down. Polyatomic ions can be counted as a unit, and I'll show you an example of what I mean. You don't have to, but they make things easier if you do. So again, let's look at some examples. Methane, so this is actually the one we looked at before, but let's look at it a little closer. So if it helps you, especially at the beginning, to make a little chart, of course the arrow is your dividing line because your reactants and products. So what I do is figure out how many of each element I have to start with. So you can see here I've got 1 carbon, I've got 1 times 4 or 4 hydrogen, and I've got 1 times 2 or 2 oxygen on the left. On the right, I've got 1 carbon, I've got 2 hydrogen, and sometimes I like to keep, if they show up in 2 places, I like to keep them separate because you can change one without changing the other. So I've got 2 oxygen plus another one makes it 3. So obviously it's not balanced. So like I said, I would start, so there's nothing really complicated here to start with, but I would leave the oxygen for last for 2 reasons, because it shows up in 2 places on the right, and also because it's by itself on the left. So it's going to be good to save that for last. So let's start, and of course the carbon is already balanced, so we don't have to do that. So we're going to start with the hydrogen. So if we put 2 in front of the water, notice that what's happened on the product side. So now I have 2 times 2 hydrogen, or 4 hydrogen, and I have the 2 from the CO2 is the same, but now I have 2 times 1, or 2 oxygen with the water, and so now I have a total of 4. So the hydrogen are balanced, the carbon's balanced, so now I just have to balance the oxygen. So on the left it's 2, on the right it's 4. So if I put a 2 in the oxygen, that's balanced. All right, let's continue with another example. All right, so determine if this equation is balanced, and if not, add coefficients to balance them. So aluminum plus iron oxide gives us iron plus aluminum oxide. So we can see on the left 1 aluminum, 3 iron, 4 oxygen. On the right, 2 aluminum, 1 iron, 3 oxygen. So of course they're not balanced. This time we're going to do our oxygen first. The reason is because the iron and the aluminum are all by themselves, so they're going to be really easy to fix in the end. So we have 3 oxygen on the right and 4 on the left. How can we balance this? Well, if you can't tell, the best thing you can do, what you need is your least common multiple. So in this case, it has to be 12. So you're going to want to get 12 on both sides. So if you multiply the right, the AL203 by 4, you'll get 12. And if you multiply the FE304 times 3, you'll get 12 on that side. Again, the coefficient has to go in the front of the whole thing. So now on the left, we have 9 irons and 12 oxygens. On the right, we have 8 aluminums and 12 oxygens. So the oxygens are balanced. But hopefully you can see the iron and the aluminum are not, but that'll be very easy to fix. So if we put an 8 in front of the aluminum on the left, and a 9 in front of the iron on the right, we balance out all the others. And so this is a balanced equation. All right, balance the following equation. O2 plus SO2 gives us SO3. This one's a little bit more difficult because you're like, well, let's not start with the oxygen because it shows up in 2 places, but the sulfur is already balanced. So there's a couple of ways you can do it. Some people might like to see that there's 4 oxygen and 3 and do what we did in the last one and try to get 12. But notice that when that happens, you're changing both of the oxygens on the left. So, and you can do that, but then you're going to have to rebalance the sulfur and things get a little bit wacky. So the one thing that I notice is because the right-hand side doesn't have enough oxygen, I'm going to need more oxygen. The only way I can get them in this case is to have a multiple of SO3. So it may not work out, but what I'm going to do is multiply the SO3 by 2. I'm going to see what happens if I get a multiple of that. I could try by doing 3, but I'm just going to start simple and try multiplying by 2. So that's what I did here. And notice if I multiply the right by 2, I now have 2 sulfur and 6 oxygen. Well, my oxygen is still not balanced, but now also notice that I messed up my sulfur. I have 2 sulfur on the right, but only 1 on the left. So let me, before I do anything else, I'm going to fix that by putting a 2 in front of the SO2. So if I do that, now I can see that I've got 4 oxygen plus another 2, and so that did balance the oxygen. So this is balanced. If you had tried the other, if you had tried going with 12, it might have worked. You could have multiplied the right by 4 to get 12. But then what I would do in that case is I would balance out the SO2s by putting a 4 in front of the SO2, and then I would have gotten there would be 12 oxygen on the left, and there'd be 8 oxygen with the SO2s, and so you would need 4 more, and so you would put a 2 in front of the O2, and that would also be balanced, but notice it wouldn't be lowest terms. You'd have 2 O2 plus 4 SO2 gives us 4 SO3, and then reduce it down. And that would be fine if you did it that way. Nothing wrong with it. All right, so let's look at this one. And this is what I was saying about a polyatomic. If you see the same polyatomic on both sides of the equation, it's just easier to take that polyatomic and balance it as a unit. Of course, you don't have to, but it does make it a little bit easier. So you can see here I've got 1 Mg on both sides. I've got 2 Cls on the left, 1 on the right. 1 Ag on both sides. 1 nitrate on the left, 2 on the right. So I can start anywhere on this one. The nice thing about this equation is that just start somewhere and then fix whatever gets messed up. So let's say I put a 2 in front of the AgNO3 so that I can balance my NO3 groups. So what happens is that it also changes my Ags to 2. So they're out of balance, so the first thing I'm going to do is, before I do anything else, is I'm going to put a 2 in front of the AgCl to balance the Ags, and then when I do that, it also balances out my Cls, and so that balances this equation. Every once in a while we have a situation where the number of O's is odd. But of course, if you've got an O2, you need to have an even number to balance it out. And so what you can do is put a fraction, or you can clear the fraction by multiplying everything by 2. So let's look at one of those examples. So here, C4H10 plus O2 gives us CO2 plus H2O. So if we first, let's balance that. We're going to leave O's for last because they show up in 2 places on the right. So if we multiply the CO2 by 4, we'll get 4 C's. And if we multiply the H2O by 5, we'll get balance the H's. So you can see there we've done that. So we've got 4 C's, H10s. But now if you add up the O's, we have 4 times 2 is 8, plus another 5 times 1 is 5, 13 oxygens on the right. Don't forget that 5 in the front, that coefficient distributes to the 2 H's and the O. So don't forget that. That's a common mistake. All right, well, I only have 2 O2s on the left and I have 13 on the right. How the heck do I get that to be 13 on the left when it's multiplied by 2? Well, what you can do is make a fraction 13 halves. We usually in chemistry they use improper fractions. I know most math teachers don't like them, but in fact chemistry they do. So what you do is write 13 halves. So 13 divided by 2 times 2 will give you 13 again. So really it's like six and a half, right? But we use the improper fraction, 13 halves. So that's what you would write down, 13 halves, and that would balance the equation. And that's allowed. If you don't like fractions, what you can do is you can then you can put the 13 down and double everything else. So it's sort of like clearing the fractions by multiplying everything by 2. So the bottom equation is also correct, either one. All right, so let's balance the following equations. You might want to stop this video and try them yourself, and then come back and listen to me go through them. O2 plus PCl3 gives us POCl3. All right, so the Cl's are balanced and the P's are balanced, but the O's are not. This one's not too bad because if I put a 2 in front of the POCl3, I'll have 2 oxygen on both sides. And then, of course, that doubles the P and the Cl3, so I can just put a 2 in front of the PCl3. So that one wasn't very hard. All right, what about this one? P4 plus N2O gives us P4O6 plus N2. All right, so the N2s, and again, you might want to work through them, putting the numbers down below them and crossing and practicing a little bit harder without doing it just in your head, and that's fine. So I already see my P's are balanced, my N's are balanced. Oh, this one can't be hard either. So if I've got 6 O's on the right and I only have 1 on the left, I need to put a 6 in front of the N2O. But because I have 6 in front of the N2O, I'm going to need 6 in front of the N2, and then the P's will stay balanced. Okay, that one's not too hard either. All right, how about this one? AS2S3 plus O2 gives us AS2O3 plus SO2. All right, the S's are not balanced. So if I put a 3 in front of the SO2 on the right, I'll have 3 S's. And then I'll have 6 O's plus another 3 O's will give me 9 O's. So I could put a 9 halves in front of the O2, 9 halves and a 3, or I could put a 2, 9, 2, 6, which is what this is showing you. So the 9 halves multiply out by 2 to cancel out the fraction. All right, this one, ooh, that one's kind of a fun one. Okay, so if I need to put a 3 on the right hand side, 3 calcium. Wow, how many are there even in the first place? There's there's 1 calcium on the right. There are 4 hydrogen, 2 phosphorus, and 8 oxygen. On the left, I have 3 calcium, I have 2 phosphorus, and 8 oxygen, plus another 1 phosphorus, so a total of 3 phosphorus and 12 oxygen. 8 plus 4 is 12, and then 3 hydrogen. Whew, that looks really complicated. If I put a 3 in front of the calcium, the whole thing on the right, in order to balance it, I have to put a 3 in front of that whole thing. So I've got 3 calcium, and then I'll have 4 times 3, I'll have 12 hydrogen. I'll have 2 times 3, 6 phosphorus, and I'll have 8 times 3, 24 oxygen. So we really don't want to change the left-hand side, the calcium 3 phosphate anymore, because the calciums are balanced. So hopefully we can change the H3PO4 to get them balanced, so the CAs are balanced. So if we multiply the H3PO4 by 4, then we have 12 hydrogen. That will balance the hydrogen. We have 4 phosphorus plus another 2 gives me 6 phosphorus, so that will be balanced. And we have 16 oxygen plus another 8 is 24 oxygen. So that's what we need to do. So we need to put a 3 in front of the big thing on the right, and then a 4 in front of the H3PO4, and that balances everything. So just take a little practice. You might Google balancing equations and you'll find all kinds of sources and probably some practice problems too.